remember the strategy that we have. We started out with the Klein-Gordon equation, Klein-Gordon theory in the Hamiltonian formulation for special relativity. Then we did the Legendre transform. It was still special relativity, but now in the Lagrangian formalism with the action. And now we are about to introduce curvature. Our further aim will be then, once we have that, to take a Legendre transform back into the Hamiltonian formalism. So this is where we are today. So step 2 was this. Step 1, step 2. So we started with the Klein-Gordon action in special relativity, and then generalized that to general relativity. So here's the Klein-Gordon action. The commas denote partial derivatives. And I've introduced now a potential here. A potential for the Klein-Gordon field, V of phi, and there are also little phi's, and they could be any other kind of field. It is believed that in cosmology, a Klein-Gordon field played a crucial role, namely the inflaton field. And that inflaton field, one way or another, nobody quite knows yet exactly how, should be coupled to all the other fields, such as electrons, quarks, photons, and so on. So there ought to be some interaction potential there that involves both the Klein-Gordon field and the other fields in nature. This is the Klein-Gordon action as it is correct in special relativity. There's no curvature, and if you choose your coordinate system to be rectangular for an inertial observer. So you see there are lots of strings attached to this action. It's correct if there's no curvature. If you are an inertial observer and you choose Cartesian coordinates, then that's the action here. Then we upgraded that action, and we said we want to rewrite the action in such a way that it is usable in flat space-time, but for arbitrary coordinate systems. You don't have to be inertial anymore. In fact, your coordinate system could be curved, no, not curved, could be organized in any which way you want. Could be mixing space and time in a wild way. And we found that this can be done if we write the action in this way. We still have the partial derivatives here, and G mu nu now is the generalization of the eta mu nu. This is scalar, so there's no changes. The potential we assume here to be scalar as well. And we needed this factor of the square root of the absolute value of the determinant of the metric. Then we showed that no matter which coordinate system you choose, you always get the same value for the action. So if you take a scalar field, phi of x and t, you plug it into this expression, you get out a number, the action for that field. And if you change coordinates, then your scalar field will now depend on variables x tilde and t tilde instead of x and t. If you plug that into this functional now, you still get out the same number. Okay, so even though phi of x and t as a function may be very different from phi of x tilde and t tilde, because they differ by a change of coordinates, as a function they may be very different. But this function now doesn't care about it. It will map that function, it will map that field, independently of the coordinate system in which we represent it, into the same number, the action. So it's a scalar action. It's a global scalar. It doesn't depend on the coordinate system at all. Now, we remember that if an inertial observer sets up a rectangular coordinate system, remember this is still flat space, if an inertial observer sets up a rectangular coordinate system, then this metric tensor here, the G mu nu of x, in that coordinate system, inertial observer, rectangular, takes this form. And also the determinant of the metric is just 1, and therefore this formula reduces to the one that we had on the previous slide. But we saw that when we change coordinates to another coordinate system, let's say we go from coordinates x to coordinates x tilde. By the way, when we do that, we have four functions that we can freely choose. We can choose the x tilde 0 as a function of the x variables. We can choose x1 as a function of the x variable, x tilde 1, x tilde 2, x tilde 3. We have four functions that we can freely choose. In other words, changes of coordinates, there are as many changes of coordinates as there are four functions of four variables. And that number 4 will come up later again. So when we change coordinates from a coordinate system x to a coordinate system x tilde, then the metric eta, the representation eta for the metric becomes a more complicated representation of the metric, depending on how complicated our choice of coordinate system might be. So we have these non-trivial change of basis matrices, these Jacobian matrices that transform eta into G tilde. So in general, if you choose some arbitrary coordinate system in special relativity, then your metric can look very complicated. Its entries will be functions of space and time that can be very strongly varying. Not because space-time itself does anything funny, it's just Minkowski space, but because of our choice of coordinates. However, no matter what choice of coordinates you make, you will always find that the G mu nu is a symmetric matrix. You will always find that G mu nu tilde is G nu mu tilde. And the reason is that this thing starts out symmetric in alpha and beta, and then we multiply the same matrix on the first index, the alpha, and on the second index, the beta. These two matrices are the same, so we preserve the symmetry of it. This then leads to a key question. Namely, do all the metrics arise from eta mu nu by a change of coordinates? Do all possible matrices G mu nu of x, or complicated matrices G mu nu of x, matrix-valued functions, do they all arise in this way from a change of coordinates? So if you start with the eta here, can you generate every symmetric 4x4 matrix valued function by choosing your coordinates appropriately? Well, the answer is no. Just noticed that I changed the slides last night, but this seems to be an older version of the slides. I don't know why it did that. That's a pity. Can't do anything about it now. Let me just, sorry for the interruption. Let me just quickly check if there we go. You see it has two conflicted copies of it. So let me just. Sorry? Yeah? Yes, exactly. It had two conflicted copies in a Dropbox. And now I downloaded the other. I think this one will probably, well, hopefully this is the good one. We'll see. Yep, that's the good one. Okay. So the key question is, can any arbitrary function obeying this symmetry condition arise from the eta matrix by changing coordinates therefore through a transformation like that? And the answer will be no. And this is an opening. This is the opening that allows us to introduce curvature. So how does this work? Let's do this carefully. First of all, let's start with the observation that no, as we will see, as I will prove in a moment, no, not every g mu nu of x tilde can arise from eta by suitable change of coordinates. What that means is that the set of all g mu nu matrix-valued metric functions decomposes into equivalence classes, where we may call two metric functions g mu nu of x equivalent if they differ by a change of coordinates. And so this statement that not all g mu nu of x arise in this way is simply the statement that the equivalence class, which contains eta, doesn't contain all of the possible metrics. So if you write down just by hand, you just pull out of the hat a matrix-valued function g mu nu of x, then you are automatically describing an equivalence class of metrics in this way. Namely, one member you already have of that equivalence class, it's the metric you wrote down. But then you can change coordinates in every possible way. And then you get a lot of matrix-valued functions g mu nu of x, and they all describe the same space-time. So that's why we put them into one equivalence class, because they're just representations of the very same space-time. Let's write such an equivalence class with a square bracket. So you give one g, and then by one matrix-valued function g mu nu of x, and then by applying all possible changes of coordinates, you get all the other members of that equivalence class. So that's a curly bracket. It's a set of all g mu nus that are obtainable through changes of coordinates. In other words, through differentiable changes of coordinates, which is also called diffeomorphisms. Then the terminology that one uses is captured by this definition. Each equivalence class of metrics is called a Riemannian structure or a Lorentzian structure, depending on the signature. If this is an indefinite signature, so if we have space and time, then we would call this a Lorentzian structure. And if it's a definite signature, so it's just plus signs, plus one, plus one, plus one, plus one, for example, if it's just space alone, then we're dealing with Riemannian manifolds. And the equivalence class of those metrics is then a Riemannian structure. So what that means is that we should think of a space-time as being described not by a metric, but by an equivalence class of metrics that differ only by changes of coordinates, by diffeomorphisms. In other words, a space-time is described by a Lorentzian structure. A spatial manifold is described by a Riemannian structure. These things are easier said than done. It's not easy to write down the entire equivalence class. If you want to nail down what exactly a Riemannian structure is, that's not easy. In general, it's very difficult to find out, even if two matrix-valued functions g mu nu of x, g mu nu of x tilde, it's very difficult to find out whether they are even in the same equivalence class, because you would have to try out all possible diffeomorphisms to map from the one to the other. It's one of the reasons why quantum gravity is hard. It's because we have to quantize those equivalence classes. These are the degrees of freedom of gravity, the equivalence classes. We're looking at the dynamics of space-time, which is not the dynamics of the metric. It's the dynamics of the equivalence classes of the metrics. And since we can't really efficiently pinpoint what is in and what is out of an equivalence class, we don't really know how to quantize efficiently. I mean, not for lack of trying. There are, of course, attempts at doing this. So let us then ask, how many Lorentzian or Riemannian structures are there? So far, I think I may not even have convinced you that there is more than one. I mean, could it not be that the equivalence class of eta is all of them, all of the G mu of x's. Let's see. How many independent degrees of freedom will there be in a space-time? Concretely, let's ask, in a metric, how many of the component functions of a metric tensor are really independent? How many can I choose independently? What I mean by that is, imagine your task is to cook up a beautiful new space-time. So you write down a G mu of x. Task done. And then somebody else says, okay, I give you another $5 if you cook up another beautiful new space-time. So you write down a G tilde of x. But it might just be the same one as the one that you had written down previously. There may be a diffeomorphism between the two, right? And then you wouldn't be eligible for your $5, I suppose. So the question is, how can we parameterize, how many parameters are there to at least parameterize those Lorentzian structures? In other words, I can choose, in principle of the metric tensor, all of its components independently, except that it has to be symmetric. But there is some redundancy in that choice, because diffeomorphisms, changes of coordinates, provide equivalences. So let's do a little bit of counting here to find out how many components of the metric tensor can really be chosen freely, and therefore how many ways are there to identify these equivalence classes, to choose one of those equivalence classes. Okay, so let's start. In n dimensions, in an n-dimensional space-time, the metric has n squared component functions because it's an n by n matrix. But of course I cannot choose those n squared functions independently because the metric always has to be symmetric. Now that cuts down the number of independent component functions to n times n plus 1 half, right? And remember why that is? It's n squared is the number of component functions that we have in total. If we take half of that, then we take into account that the upper triangle of the matrix is identical to the lower triangle of the matrix. And as far as the diagonal is concerned, we took only half of it, right? So we have only half of the diagonal, but of course there are degrees of freedom on the diagonal as well, so we have to add n half. That's the extra term here, n half. So it's n squared half plus n half. So the number of degrees of freedom in a symmetric n by n matrix, the number of independent components in a symmetric n by n matrix is n times n plus 1 half. Are they really independent? Well, yes, you can choose them independently, but if you make two different choices, you may still describe the same space-time, right? So we have to mod out. We have to take into account that we have these equivalence classes. In other words, some of those components of a symmetric G mu nu matrix, valued function, some of those components can be chosen to take any value you want, independently of which space-time you want to describe. And that's because you have freedom in choosing your coordinate system. So in particular, if we go from one metric to another metric, we have those matrix-valued functions that change the coordinates around. And how many functions, how many degrees of freedom, how many functions do we have of arbitrariness in doing this? Well, we have n of them, right? Because we have the x tilde 0 is a function, x tilde 1 is a function that we can choose, x tilde 2 is a function that we can choose, and x tilde 3 is a function we can choose. In general, if the spacetime has n dimensions, there are n functions we can choose freely, and therefore that we can use to manipulate the entries of the metric to arrange that particular entries take particular values, just by virtue of changing coordinates. And that means that of those n times n plus 1 half degrees of freedom, freely choosable functions, really freely choosable, are only n times n plus 1 half minus n. So the overall number of degrees of freedom, of continuous degrees of freedom, is this. See, we did a count of continuous degrees of freedom. You can also change signature, right? If you change signature, that's in a whole different league. Okay, so the number of independently choosable functions in the metric modulo changes of coordinates is given by this expression, which is n times n minus 1/2. And for example, for our space-time of 1 plus 3 dimensions, as far as we know so far, n is equal to 4. And therefore, we have 4 times 5/2, that's 10. Minus 4 is 6. So this means that in order, there's a 6-parameter family of those 6-function family of metrics in 3 plus 1 dimensions. So in that sense, gravity has 6 degrees of freedom. Now for n equal 2, that's another very interesting case. That could be either 2 spatial dimensions or 1 space and 1 time dimension. For n equal 2, let's also go through it. Well, then we have 2 times 3 is 6. Half of that is 3 minus 2 is 1. That means that for a 2-dimensional manifold, whether it's Riemannian or Lorentzian, the number of degrees of freedom is really only 1. Curvature for a 2-dimensional surface is really only 1 degree of freedom. In other words, scalar is scalar. Curvature in 2 dimensions is scalar. Sure, there are curvature tensors, all the objects that we will describe in the next slides, but you can describe them completely with just one scalar function. That's special about 2-dimensional curvature. But it's also a challenge for us because whenever we think of curvature, intuitively, it's about 2-dimensional curvature, right? Because can you imagine something 3-dimensional that's actually curved in 4 dimensions? That's tough. So, so the curvature that we have intuition for is really 2-dimensional curvature, and that's a scalar entity. It's fundamentally a scalar. Oh, and we also see that there is no curvature in 1 dimension. There's no degree of freedom of curvature in 1 dimension. Yep. Yep.
Is there anything special that the degrees of freedom are equal to the degrees of freedom of an antisymmetric matrix?
I don't know. You're right. I mean, basically your point is that this is n times n minus 1/2, which is the number of degrees of freedom of an antisymmetric matrix. I don't know. I don't know. Yeah, but the curvature tensor has 4 components, and the 2-component Ricci tensor is not covering all of the curvature. Well, let's keep that in mind. Maybe we'll see something like that. It's an interesting observation. Okay, so what is curvature anyway? So far we just talked about the metric, and the metric just gives us means to calculate distances, invariant coordinate system independent distances. So the issue about curvature becomes pressing for the following reason. Let's slowly get to that. So we continue, first of all, now that we allow g mu of x's, which are not in the same equivalence class as eta, we allow curvature, right? I mean, I haven't really explained curvature just yet, but that's what we are going to allow now. So this g mu of x generally may not have a representation as eta for whatever coordinate system you may want to choose. Then, in fact, we will allow almost any g mu of x. However, we will want that there ought to be a change of coordinates for every point on the manifold. There ought to exist a change of coordinates such that at that point at least, the metric in that new coordinate system takes the form eta mu nu. Okay, so it's a subtle thing. We do no longer require that there exists a coordinate system such that in that new coordinate system, g mu nu takes the form of eta mu nu for all x at once. We don't require that anymore. If we required that, we would be back to special relativity. But what we do require is that the g mu nu is not just any arbitrary symmetric n by n matrix valued function. No, we want that it's such a symmetric n by n matrix valued function. It's such a function so that for every point on the manifold, there is a change of coordinate system such that at that point of the manifold, in the new coordinate system, the metric takes the form of special relativity. This is the statement of the equivalence principle. Because what it says is that we may not have special relativity globally, but we require special relativity locally. We require that at every point, there is a coordinate system that you can choose such that at that point, this is the metric, and therefore close to that point, the metric is not all too far away from that. So this means we postulate that gravity can always be locally eliminated, at least at a point. We cannot require that gravity is locally eliminated in a finite region, because any finite region will have the ability to detect tidal forces. But at a point itself, there are no tidal forces. And you know what I mean by tidal forces? It means that gravity acts with a different strength here than there, and therefore there is a differential in the force, and that rips on the object on an object of finite size. Okay, so we require that gravity can always locally be eliminated. This is, of course, a slightly non-trivial thing quantum mechanically, because you know how hard it is to localize a particle at a point. If you succeed, I mean, you will never succeed because it's an infinite amount of energy, but if you could localize it very much, the particle would very quickly, once you let go of it, it would very quickly have its wave function spread out very far. And so you can't really implement that in quantum mechanics. Particles are always having some extent, so they will always have, to some extent, access to tidal forces. But as far as the classical theory is concerned, we want that a freely falling observer in a small region who sets up a rectangular coordinate system will basically experience life as if it was in special relativity. So that, in other words, the coordinate system in which special relativity holds will be, because special relativity holds, it will be a freely falling coordinate system. It will be a coordinate system in which the observer doesn't see any pull or push in any particular direction. It will be freely falling, as if the observer was inertial in special relativity. But again, only very locally. Of course, gravity is often so small that you can almost neglect the tidal forces, and then this region in which effectively special relativity holds may be rather large. But as a matter of principle, we only require it at a point. Oh yes, and for this to be true, I mean, this is what guided Einstein to this principle, of course. For this to work, any object's gravitational mass must be equal to its inertial mass, so that all bodies would fall equally, so that one observer's coordinate system in which the metric takes the form eta is also another observer's coordinate system in which the metric takes the form eta. The way we defined this was not making any reference to what kind of object you may want to put at a particular place on the manifold. Okay, so then how can we identify the presence of curvature? If somebody gives you a metric, g mu nu of x, and you're supposed to find out whether or not this is a flat space-time, then in principle you could try it the hard way. You could check whether there are diffeomorphisms that map your G mu nu of x into eta. If there aren't any, you know that it's not Minkowski space. If there is one, you know it is Minkowski space. But this is really the hard way to do it, because how do you write down all possible diffeomorphisms, all possible changes of coordinate system? There is a better way. So assume we're given the metric tensor G mu nu of x as an explicit matrix-valued function in some coordinate system. Now, how can we determine whether or not this is, for example, flat space-time written down in some funny coordinates? This problem can be solved by using methods of differential geometry. First of all, you take your metric of which you want to know whether or not it's Minkowski space. You take your metric and you calculate that complicated expression, the so-called Christoffel symbols. And then once you have those, you can then define the Riemann curvature tensor. And you see why the Christoffel symbols had to be defined, because otherwise, you know how long that expression would be for the Riemann curvature tensor in terms of the metric directly. It would be very long, right? Because this stuff is actually those terms squared. So that would be 9 terms plus 3 plus 3. 24 terms. So this Riemann curvature tensor now is important because it expresses the curvature itself. I hope that you all have some background in this, but let me quickly go through the significance of it. So a space is called curved at a point x if the parallel transport of a vector along an infinitesimal parallelogram returns the vector to the original starting point, but with a rotation. So imagine this is a point on the manifold, and then we do a parallel transport in the direction of some vector eta, then in the direction of some vector nu, and then backwards parallel transported. So this is the parallel transported to this one, that's parallel transported to that. Then as we parallel transport the vector this way, that way, that way, and this way, the vector arrives back, but it may point in a slightly different direction. And that change of direction is this v minus v prime vector. That v minus v prime vector can be expressed in terms of the Riemann curvature tensor in this way. You take the Riemann curvature tensor at the point x, then multiply it or contract it with the vector that you want to parallel transport. And you also contract it with the vectors that describe the parallelogram's shape. And the first two coefficients are there to contract with the two vectors that describe the parallelogram's shape. And this component is to be contracted with the vector that's parallel transported. And then that component is the change of direction vector. In other words, once you hold fixed the two vectors that describe the parallelogram, once you've contracted that, then you're just left with a matrix R that has two indices, A and D, left over. And that's an infinitesimal rotation matrix. You take that vector, and then this is the rotation that this vector experiences. See, these are infinitesimal parallelograms, and so the rotation is also an infinitesimal one. That's an infinitesimal rotation matrix then. Actually, in general, it's not a rotation, but a Lorentz transformation. But if it were just a spatial curvature, then it would be just a spatial rotation. If it's in space-time curvature, then it will generally be a Lorentz transformation. Okay, so we can calculate that effect. And that effect, namely that in the course of an infinitesimal, of a parallel transport along the boundary of an infinitesimal parallelogram, the fact that this will rotate or will not rotate vectors that we parallel transport, that is, of course, a coordinate system independent statement. In other words, when we calculate that Riemann curvature tensor, then if the space-time really is Minkowski space, this better comes out 0, right? Because on Minkowski space, a vector parallel transported on a parallelogram will come back parallel to itself. Only on curved space may that be violated. In other words, all you have to do in order to find out whether a metric tensor, G mu of x, is equivalent to Minkowski space or not, is calculate from the metric G mu of x the Christoffel symbols, plug them into the metric tensor. If all components come out 0, then it's Minkowski space. But if any one of them comes out not 0, then it's not Minkowski space, and instead it's a curved space-time. It could also be, in principle, that the parallelogram doesn't even close. That could be that if you go this way for some distance and then that way some distance, and then here the parallel transported vectors, could be that you don't arrive at the same point, going the lower way or the upper way. In this case, we would say that space-time has torsion. There is no evidence, no positive evidence that space-time does have torsion. Einstein thought that it might explain electromagnetism, but it was a dead end. The assumption today is that there is no torsion. The evidence is simply not there. We don't have any reason to introduce torsion. And it has been tried to make sense of torsion in terms of electromagnetism and other things, and that hasn't worked out. So that's the status of that. So now here's the proposition, I said it already, that if in a region of the space-time, the metric, the curvature tensor vanishes for all points, well then in that region there exist coordinates such that the metric tensor takes the form of eta because it's flat. It's a curved space-time that has just no, I mean, it's a space-time that has no curvature in that case. And if it does have curvature, then of course the Riemann curvature tensor does capture the amount of curvature that it has. By the way, I should say that the curvature tensor is obviously a tensorial quantity. And for us, it is difficult to get intuition for what tensorial curvature might be, because we only have the intuition from 2 dimensions, and in 2 dimensions, curvature is scalar. And what is it, by the way? Well, if you have a 2-dimensional manifold, then at any point, if you want to know what the curvature is, you can imagine putting a ball there, a sphere there, that approximates the manifold optimally at that point. Basically, so that the second derivatives manage. I mean, the first derivative is a tangent, right? The second derivative that they match. And then you can ask what is the radius of that sphere, and that gives you a measure of the curvature. So is there anything similar to that in higher dimensions? And there is. And the reason is that through every point, even of a higher dimensional manifold, through every point, you can think of putting a 2-dimensional manifold through it. Even if the entire manifold has 26 dimensions or 180, doesn't matter. At every point, just choose a 2-dimensional surface that goes through that point. And then for that 2-dimensional surface, you can define how curved it is. And then you choose another 2-dimensional surface, and another 2-dimensional surface, and another 2-dimensional surface, and so on. And so you choose orthogonal surfaces, and then you measure what curvature they have, and that's another way of capturing how much curvature there is at a given point. These curvatures that I just talked about, you put 2-dimensional slices to a point, are called the sectional curvatures. And so there is a way to express gravity in terms of sectional curvatures. There is a way to express the Riemann curvature tensor in this form. It's basically, if you take the Riemann curvature tensor, and you pull down that index here, no, sorry, you pull that one up, then you have if I remember correctly, then you have that it's antisymmetric in those two indices, antisymmetric in these two indices. And what that means is that the Riemann curvature tensor then becomes a map of antisymmetric two tensors into antisymmetric two tensors, because you can contract with those two indices, antisymmetric object, you can contract with this, and you get another antisymmetric object out of it. And in the case of Riemannian signature, not Lorentzian signature, but in the case of Riemannian signatures, the eigenvalues are the sectional curvatures. The eigenvalues of that map, the Riemann curvature tensor viewed as a map. All right, so now the dynamics of space-time. So what are the equations of motion for space-time? For its metric, for its curvature? Now, in principle, we want to know the equations of motion for the Riemannian structures, or the equations of motion for the Lorentzian structures. But we are not so fortunate. What we'll have to make do with is equations of motion for the metric tensor, even though that is containing redundant information. Redundant because its modulo changes of coordinates. So what we can do is we can look for equations of motion for the metric, G mu nu of x. And if we do that, it's non-trivial because, as I mentioned already, it's non-trivial because G mu nu of x contains two kinds of information. If G mu nu of x looks complicated, it can look complicated for two very different reasons. G mu nu of x can look complicated because even though space-time may be flat, no curvature whatsoever, or just very little, it could be that the coordinate system is chosen in such an intricate, elaborate way that G mu nu of x looks very complicated. Or alternatively, it could also be that space-time really is very much curved, and therefore there is no other way. G mu nu of x has to be very complicated, just because space-time itself has a very complicated structure. And so given an arbitrary G mu nu of x, it's not easy to find out if it's complicated looking, why that might be. And that's what makes it difficult to quantize the metric, because we only want to quantize the actual degrees of freedom, the actual shape of the space-time, and not the choice of coordinates, because choices of coordinates are human-made. Why would we want to quantize our choices? Right? We have to quantize the degrees of freedom themselves. And remember that not only the G mu nus are coordinate system dependent, also the R mu nus don't really help us all that much. You see, the Riemann curvature tensor is also itself coordinate system dependent to some extent. It is true that we can always use it to identify whether or not we live on a flat space, because only then and only then will this thing actually vanish in a region. But if it doesn't vanish, then the actual entries of the Riemann curvature tensor very much depend on the choice of coordinate system that you make. Because it's tensorial, so you know that this transforms. Now, we need something, of course, that does not depend on choices of coordinates. So what we need is a coordinate system independent action for the metric, so that we can then formulate the equations of motion, again, in a coordinate system independent way. Simply by the usual action principle. We want some scalar function of the metric, and then the variation, the variational derivative, the functional derivative with respect to the metric of it should vanish. So we need to find a scalar that depends on G, but that we can use for the action. Now, we'll we'll start with the Riemann curvature tensor. That's a good starting point because we know that it is more reliable than the metric in the sense that the Riemann curvature tensor vanishes only if the space is really flat. And in any case, the Riemann curvature tensor can be expressed entirely in terms of the metric. So it's all there. But the Riemann curvature tensor has 4 indices, and that's too many. That's not even close to being a scalar. So in the next step, we define the Ricci tensor. The Ricci tensor is the contraction of the Riemann curvature tensor where those 2 indices are contracted. I is running from 0 to 3, so that it's all covariant. And remember that we have the Einstein summation convention that twice occurring indices are to be summed over. Now, other index contractions in principle are possible, but they would vanish because of the antisymmetries and symmetries that are inherent in the Riemann curvature tensor. There's really only one way to cut the 4 indices down to 2 indices without it all going to 0. So we have the Ricci tensor here. And it turns out that as we do this, as we restrict, as we take this contraction, we are losing information. You see, if you're given that tensor, you cannot reconstruct what this one is, because you cannot undo a summation, right? If you're told that the sum of 2 numbers is 8, you don't know whether that's because somebody added 4 and 4 or somebody added 3 and 5. And so in principle, it is possible that the R mu nu does not contain all the information that the full Riemann curvature tensor had. And that is indeed the case. It is possible to have R mu nu equal to 0. The Ricci tensor may vanish even when the full Riemann curvature tensor does not vanish. Actually, what's missing is the so-called wild curvature. This is a Ricci curvature, and there's an extra tensor, so-called wild tensor, that contains the missing information. For example, gravitational waves are described by wild curvature, and they are not captured by that. This is the curvature that will couple to matter. The wild curvature does not. Wild curvature is curvature that can exist in free space, in the vacuum. Ricci curvature always needs matter. Where there is no matter, there is no Ricci curvature. Basically because this is proportional to an expression in terms of the energy momentum tensor, as we will see. All right, so, but, you know, we really don't have any other choice to proceed. We have the Riemann curvature tensor, then we contract it in the only way possible to get down to 2 indices, and then we're left with that. We need a scalar for the action, so really no choice. And then we define, out of this Ricci 2 tensor here, the Ricci scalar. So finally we have a candidate for the gravitational action. Now the simplest scalar that can be formed from the metric is, of course, simply the contraction of the metric with itself. But that's just 4, right? Because if you contract G mu nu with G nu alpha or something, then you get a Kronecker delta, because the G with the upper index is the linear algebra inverse of the G with the lower indices. So you get an identity matrix and a trace of it, and that's just 4 for space-time. So that's really the simplest scalar that you can build in gravity. The next simplest scalar that you can build is this one. And then you can build any number of other scalars if you allow yourself to use several copies of the Riemann curvature tensor and the Ricci tensor. Then you can write down expressions like this. That's a scalar, all right. But you see, it's going to be much smaller than that. Generally, gravity is usually quite weak. Compared to the other forces, it's more than a dozen orders of magnitude weaker. It's very weak. And so, even when that is of appreciable size, you see the square of expressions in the curvature tends to be even smaller. So you can build this scalar, you can build scalars by taking 3 copies of the Riemann curvature tensor and then contracting them in different ways. There's an infinite sequence of terms that you can write down that are all scalar and all dependent on the Riemann curvature tensor. At some point, they become dependent on each other. And there's just like, I don't know, a dozen or so of truly independent scalars that you can build. But we expect, as far as the sizes are concerned, because of the sizes, that this would be the dominant term. Or actually, this one, constant. So what then could the gravitational action be? Well, a priori, the full action should look like this. The total action of everything in the universe, would be an action for the Klein-Gordon field, an action for other fields, and these actions should include the interactions between them, and also an action for gravity. Now this stuff we can look up in the standard model of particle physics. But the gravitational action, a priori, we should expect to take this form. It should start out with a constant, because as we established in the previous slide, the simplest scalar you can build is just the identity, just g mu nu, and then plus some other constant c1 times the Ricci scalar, plus some other constant c2, and then we have contractions of higher order curvature terms, and more higher order curvature terms, and so on. Everything multiplied with the square root of g factors, so that the whole thing really stays scalar. Remember that even though you might put scalars in here, it doesn't mean that S is scalar, because you need this. Otherwise, when you change coordinates, the volume correction, the Jacobian, it would not be compensated for. See, if you change coordinates, this number does not change when you change coordinates. But the measure changes by Jacobian factor, and this changes by the inverse of the Jacobian factor, so the whole thing is a scalar. All right, now, comparison with experiment shows that there's really only evidence for the first 2 terms. A constant, which is now called the cosmological constant, and the Ricci scalar term, which is the Einstein action, which gives us the Einstein action. Now, this is fortunate for several reasons. One reason why this is fortunate is that, well, we don't really want to deal with these higher order terms, because they could be really messy. But secondly, if there were higher order terms, it would really throw into question all we know about dynamics. Because generically, those higher order terms screw up everything. If you have higher order terms in there, and then you calculate what the Euler-Lagrange equations are, you will find that those Euler-Lagrange equations are not second-order differential equations. They're not of the hyperbolic type. They're no longer of the type where you can say initial condition, this is the metric, that's its rate of change, and then we can calculate the evolution of it. We wouldn't have a well-defined initial value problem of the kind that we're used to in physics. In physics, we're used to only needing to know initial conditions of the form amplitude and derivative, and then we can go, right? Like in mechanics, you know where a stone is, you know what the initial velocity is, you can calculate its trajectory. But that might require that you know all of its derivatives already, right? Or something weird, or it might not even be determined. The future may not be determined from the initial conditions. So it's good that we don't have actually positive evidence for these terms experimentally. However, the quantum theory, as far as we understand quantum gravity, if you just straightforwardly apply quantum theory, it will induce higher order terms. It will induce that problem. We still have to address why that's not screwing up the predictability of GR. Anyway, what I just said is true for 3+1 dimensions. However, in higher dimensions, it is possible to add extra terms to the to the action without screwing up the usual predictability of a theory. So you can still have a second order differential equation in time so that you can set initial conditions, value and derivative, and so on. That is actually possible. This was calculated by David Lovelock, who was here at the university in the applied math department. That was done in the early 70s. So if you work with higher dimensions, you may want to look into higher order terms. They do not necessarily screw things up. But you have to choose them very carefully for in order not to screw up the nice dynamics that we know from other theories in physics. Okay, so what are then the equations of motion? Remember, the total action has contributions from the Klein-Gordon field, from all other fields, such as electrons, photons, quarks, gluons, the whole thing. It has contributions from, the Klein-Gordon field, all the other fields, and from gravity. Correspondingly, we get several sets of equations of motion. If we vary the total action with respect to the other fields, then we get the classical equations of motion for them. If we vary the total action with respect to just the metric, we get the Einstein equations. And if we vary the total action with respect to the Klein-Gordon field, later the inflaton field, then we get its equation of motion. So let's go through this A, B, and C one after the other. So if we take the total action and functionally differentiate it with respect to the other fields, like electrons, quarks, and so on, then this will give us the fully general relativistically covariant field equations, such as the covariant Maxwell equations, for example. And then how would we quantize that? Well, we would still get the classical theory if we just work with the little phi fields. We would do a Legendre transform to get the Hamiltonian formulation, then impose the canonical commutation relations and go from there. Secondly, we take the total action and we functionally differentiate it with respect to the metric. And this will give us the equations of motion for the dynamics of curvature, for the dynamics of the metric. And these are the equations of motion that we get, assuming that there are only those two leading terms in that curvature expansion, only the cosmological constant and the Ricci scalar. Then this is the Einstein equation. The actual calculation of the Einstein equation from the action, I leave to you as an exercise. It's in Mokanov's textbook, Mokanov-Vinitsky. What's very important to keep in mind here is that G mu nu occurs all over the place in the action. It occurs not only in the Ricci scalar. G mu nu occurs whenever two indices need to be contracted. So G mu nu occurs all over the place in the action of the electromagnetic field, in the action of the spinors and scalars. Everywhere the metric creeps in, and the contribution to this equation that comes from varying just the Einstein action, just the Ricci scalar, that contribution gives us this. The terms that arise from differentiating the Einstein action with respect to the term with the cosmological constant gives us this term. And then all the other occurrences of the metric spread throughout the action of the various matter fields that there are in nature. Those contributions will give us the energy momentum tensor here. They're just collectively called the energy momentum tensor. It's the definition of what the energy momentum tensor is. And often that term is written on this side here. And then we can interpret the energy momentum, we can interpret the cosmological constant as contributing to the energy momentum tensor. So again, if you functionally differentiate just the gravitational action with respect to g mu nu, you get these terms. If you differentiate the action of the Klein-Gordon field and the other fields with respect to g mu nu, you get the energy momentum tensor. Now, what is it explicitly, the energy momentum tensor? For the Klein-Gordon field, I mean, there are lots of contributions, but as we will see later in this course, for cosmology, most important is going to be, luckily, the energy momentum tensor contribution that comes from the scalar field. There are specific reasons for why the other fields are not going to contribute as much very early in the universe. So luckily, we get away with studying this scalar field. Apparently, scalars are particularly important for cosmology. And then when you calculate the energy momentum tensor for a scalar field, so all you have to do is take the Klein-Gordon action and functionally differentiate it with respect to g mu nu. Then you get this long expression here. Notice that there are first derivatives, but in a different index structure, and the potential. And what will become very important later on for cosmic inflation is the fact that when you put the cosmological constant here on the right-hand side, then it will contribute a diagonal term to the energy momentum tensor. It will contribute to the energy density and to the pressure. And if you now look at the Klein-Gordon field's energy momentum tensor, then you will see that the potential contributes in the same way that the cosmological constant does. You see why that is? It's because the V multiplies the G, right? So the V multiplies the G, therefore contributes to the energy momentum tensor the same way that the lambda multiplying the G. Which means that, just a sec, which means that when the inflaton potential, when the scalar field's potential is very large compared to the other terms in here, then the energy momentum tensor of a scalar field does the same thing as does the contribution of a cosmological constant. And we do know that a cosmological constant, a positive cosmological constant, will make the universe explode exponentially. And that is what a Klein-Gordon field can do too. When a Klein-Gordon field has a very large potential, value of its potential, then it is as if there were a very large value of the cosmological constant. And that means that it leads to an expansion of the space-time. So what the standard model of cosmology now is saying is that if you have a Klein-Gordon field, then just by chance it might happen that locally, in some patch of significant size, the field phi might fluctuate such that the potential fluctuates to a really large value, just temporarily, just in a small patch. But if it does so, then for the quantum field and for general relativity, in that patch, it is as if there was a large cosmological constant. And that patch starts blowing up very quickly. And that is how a universe can spawn another universe in an inflationary process. Anyway, we'll do these things in more detail later on. You had a question?
Sorry, so just to be clear, the reason why you said cosmological constant is that the diagonal part, because we're assuming the framework of some walker, so the metric is diagonal. Everything is diagonal. We're assuming the framework of some walker.
True. Well, you can always diagonalize it. So basically,
no, even if it's not diagonal, you can always use some basis.
Yes, you can always use some basis. Or let's put it this way: the main point is really that I shouldn't have expressed it this way. You're right. The main point is not that it's diagonal. The main point is that the potential multiplies the metric, and so does the cosmological constant. So whatever the cosmological constant can do, the potential can do. but the potential can do it temporarily. A cosmological constant is constant, right? But so if there was a cosmological constant that dominated our universe completely, then it would always exponentially expand according to that. We know that that's not the case, even though there may be an inflationary future for us. But a potential can temporarily mimic the effects, mimic the behavior of a cosmological constant, and therefore trigger what the cosmological constant would do temporarily.
So even if it was just at the beginning of the influence field or the even though if it existed just at the beginning of the universe in some small period, we can't hold the conclusion that later on it turned into cosmological constant or something like that.
No, that's not the idea. The idea is not that it turns into a constant later. No, the idea is that it goes back to zero value eventually. And if we do have some non-zero cosmological constant in the background, it generally believed that it has some other origin. I mean, there are attempts, of course, to model the presently observed cosmological constant also dynamically. But we don't really have positive evidence for that just yet. But maybe I should just stress what outrageous idea this whole thing really is, right? It says that if you have a universe with a scalar field and a potential, then that universe is not stable. Because the field might just fluctuate to have temporarily a large value of its potential, which will mimic, even just in a small area, which will mimic a cosmological constant there. And so space-time might mushroom out and create a daughter universe of cosmic size within a fraction of a second. And our universe could, any moment, there it could spawn another daughter universe, right? It says that it's not stable because of that. Yep?
Could this be resolved if you also treat gravity quantum-like? I mean,
well, I'm not saying that it's a problem, right? I'm saying it is an opportunity to explain the origin of the universe. It might just be a daughter universe to a previously existing universe. You might have been spawned out of the nose of a dog, of a mother universe, right? I'm not saying it's a problem. Treating gravity quantumly might change the picture, but it's very hard to do. And of course, what it would imply too is that you have this infinite chain of universes spawning each other, which leads to philosophical paradoxes. Natasha?
So is this theory the same theory we would have get for the scalar field using Noether's theorem?
Sorry, the T mu nu, whether that arises from a Noether's theorem?
Yeah, you know how we define it with the variation
Mm-hmm.
with respect to the metric?
Yeah.
So what if we get the action of the scalar field and compute the stress energy?
Yeah. Right. No, can't do it because we don't have the symmetry. You see, in a curved space-time, we don't have translation and rotation symmetries or general Lorentz symmetries. So we can't do it. It's true, originally, when you first study continuum mechanics, you derive usually the energy momentum tensor using basically Noether's theorem. You say, I have this symmetry, what is it that is conserved? And you find the energy momentum tensor. And you may remember too that it doesn't have to be symmetric when you calculate it this way. Now it turns out that in general relativity, energy is not conserved. Momentum is not conserved, right? Because we don't have the translation invariance in space, we don't have translation invariance in time. That's simply not conserved, and there is no, there is an analog of Noether's theorem, but it applies only when those symmetries exist. If you have so-called killing vector fields, you get a symmetry from that, and that's then a special property of the energy momentum tensor. But a priori, there is no general conservation law. There's a balance between curvature and energy and momentum. So it's really a genuinely new way that the energy momentum tensor is calculated, by calculating it as the functional derivative of the action with respect to the metric. And you always get it symmetric in this way, because you differentiate with respect to a symmetric G mu nu. That's a different way of doing it. And you can, however, show that it will give you the same thing if there is symmetry. If you have an Noether-Therm, it will give you the same thing. Oh, and by the way, you see, the potential of the inflaton is thought to eventually decay. So initially it was a very large value, triggered it behaved like an effective cosmological constant temporarily, and then led to the spawning of a new daughter universe. But that was empty. Whatever was in that patch that inflated, whatever there was before, well, after the universe expanded by 10 to 100 orders of magnitude or something like this, I mean, it might be as large as that, then that would be completely diluted. The universe would be empty. Our universe is not empty. Where's stuff coming from? Basically from that V. The idea is that that V has to come down. That energy has to go somewhere. And so that inflaton field decays into all other species of particles. The inflaton field is thought to be difficult to produce, high mass, so it decays into lower mass particles such as photons, electrons, and so on. So actually, the potential is multi-purpose, right? It spawns a new universe, and then at the end of it, it fills it with matter. And because the whole thing is a quantum theory, it will also provide the initial inhomogeneities in the universe, around which then the galaxies condense. And of course, that's the whole purpose of this course, that we see how that's calculated. Okay. So quantization, if you wanted to quantize the Einstein equation, that would be difficult for several reasons. For example, it's difficult to separate the curvature degrees of freedom from the mere artifacts of the choice of the coordinate system, right? We want to quantize degrees of freedom of physics, and we don't want to quantize the choices that humans make. That just makes no sense. So that's a problem. You would have to distill somehow the degrees of freedom of geometry out of the diffeomorphism invariance. Another problem is that the Einstein equation is highly nonlinear. And also, you see, it looks linear in R, but if you write it out in G, it's not. Right? For G, it's very highly nonlinear. And so it's very hard. Even perturbative approaches have run into great difficulties. It seems that gravity is not what is called renormalizable. So in this course, we will initially, to make life a little easier, we will initially simply assume that a classical background space-time is given. That could be a black hole. That's what we do at the end of the course. Or it could be a Friedmann-Robertson-Walker space-time. Just, have some evolution of space-time that's given. Let's say after or while the universe is expanding dramatically because there's a temporary cosmological constant, we assume that a classical background space-time is given, and we will study the quantum physics of the fields that live on that expanding space-time. So we basically take ordinary second quantization, ordinary Klein-Gordon equation, and upgrade it to the situation where the space-time is expanding underneath it. But it's still a classical space-time. That treatment is not sufficient for cosmic inflation. So we will upgrade it then to include quantum fluctuations of the metric as well. But only to lowest order. So the linear perturbations, they will be included as well. Part of the predictions will then be temperature fluctuations, and part of them will be polarization fluctuations. And both of them have at least part of the origin in the quantum fluctuations of the metric itself. The polarizations, all of it, and the inflationarily caused fluctuations of the polarization in the CMB, trace only to the quantization of the metric, and the temperature fluctuations trace back partially to the quantum fluctuations of the metric and partially to the quantum fluctuations of the inflaton field. But I'm anticipating all this stuff. We will do this stuff in much more detail later on. Okay, and so finally then, C, we also get initially classically the equations of motion for the Klein-Gordon field by simply functionally differentiating the total action with respect to phi. That's the same as functionally differentiating the total action with respect to just the Klein-Gordon action, because the gravity action doesn't have phi in it. So we have, it's just ds of Klein-Gordon by d phi equal to 0. Where in principle there are also interaction terms with the other fields, but we will neglect that for now. In fact, what works very well for cosmology is, what matches observations very well, is to assume that in the very early universe, the scalar field was chiefly interacting with itself, with a term similar to phi to the 4 theory. Phi to the 4 itself seems to be ruled out experimentally already, but terms similar to that might do it. So then we apply the Euler-Lagrange equations. Remember, these were the Euler-Lagrange equations that we derived in the previous lecture. And from them, with some grinding through the calculations, we can get the Klein-Gordon equation. No, in fact, not much grinding. You can directly read that off, right? I mean, if you just look at ds by d phi, here we have the full expression. If we functionally differentiate with respect to phi, we get contributions from this term and that term. So we get one term that's proportional to phi, functionally differentiating this, one term that's proportional to phi to the 3rd power, functionally differentiating that. Okay, that gives us the left-hand side. The left-hand side. And then the right-hand side is obtained by functionally differentiating s with respect to the derivatives of phi. That occurs here. You get a factor of 2 because we get a contribution from this term, contribution from that term. Cancels the 1/2 over here. That's here, 2 over 2. And then we have just this one term left over. That's what we get. That's the right-hand side. So here we have the Klein-Gordon equation for general relativity. And you see it's getting much more complicated than it used to be. Let us reformulate it a little bit. So here we have just some terms that involve phi, and then there's the square root of g. Let us put this square root of g over to this side by dividing by 1 over square root, by dividing by square root of g. Then we put everything on the left-hand side, and we find that the Klein-Gordon equation now looks like this. Complicated stuff involving derivatives plus m squared phi plus this self-interaction term equal to 0. Without this term, it would have been the ordinary Klein-Gordon equation. In fact, if you set g to eta, this becomes the ordinary Klein-Gordon equation again. But this is curved space. Life is harder now. Still, this is a second derivative, though. At least it contains second derivatives, because the comma here means a first derivative to be taken by phi. This is d phi by dx nu. And you multiply, and then here's another derivative. So what you see is that we will definitely get second derivative terms. We will also get first derivative terms, though. So the Klein-Gordon equation is much more messy now on curved space. But overall, what we see here is that there is some complicated differential operator that involves first and second derivatives acting on this poor function phi that has to endure all those derivatives. Okay, so let's identify that differential operator here and give it a name. So that's the box. That's the new D'Alembert operator. It's all of that differential stuff that's acting on the phi. And then we can write the Klein-Gordon equation in this form, so at least it looks simple now, even though we know very well that this thing is non-trivial. All right. So now we are here. We did this step. We now have the Lagrangian formulation. We can do Klein-Gordon, other fields, and gravity fully covariantly in the Lagrangian formulation. Our next step will be to do the Lejeune transform to the Hamiltonian framework, identify what the canonically conjugate momentum field is to phi, which will be quite non-trivial, and then we can do the proper quantization and apply this to cosmology. Let me just give you a quick hint for another path that one can go, and later in this course we will do this in 1 hour. we can also start from where we are now and then quantize everything directly without ever going back to the Hamiltonian formalism. And that was cooked up by, goes back to Feynman, of course, Feynman and Dirac and Schwinger. Okay, so this is just a quick preview for this path, where we just go directly from first quantization to second quantization by using the path integral. And then that formulation is actually equivalent to this formulation because they lead to the same differential equations, the so-called Dyson-Schwinger equations. Dyson-Schwinger equations are the equations of motion for correlation functions. And ultimately, in quantum field theory, everything boils down to correlation functions. So if they are to obey the same differential equations, then it's the same theory. Okay, so how does one do the second quantization with the path integral? Let's assume that we are given a fixed space-time background. So let's say it's a FRW space-time, for example. Then we assume that the classical G mu nu of x is given, and we're supposed to work with that. We're not quantizing it. We're just studying how the field lives on that, a quantum field. How does a quantum field live on that classical space-time background? So we can immediately write down what the Klein-Gordon action is. We just had it up on previous slides. And then following Feynman, we look at the following functional. We assign to every field evolution phi of x and t. It's not operator value, just number value, right? Phi of x and t, that's a field evolution, phi of x and t. I call it evolution because the t is also t dependent. For every phi of x and t, for every field evolution, we get a number. Namely, by just exponentiating the action. So e to the power of I over h bar times the action of a field evolution on the given metric background is what we may loosely call the probability amplitude for this field evolution to happen. Can't really normalize this. It doesn't really have a proper interpretation as a probability amplitude density, but it gets close to it. It's very analogous to what you have in first quantization. So what we have is a probability amplitude for a particular field evolution to happen. And then we may want to calculate correlation functions. For example, you may want to know what is the vacuum expectation value of this product. It's the field at one position at a given time and the field at another position at the same time. It's very close to what we actually want to calculate. For example, in the cosmic microwave background, we have a snapshot of the universe at a particular time. Namely, I'll get to that. In any case, it's basically a snapshot at a particular time. And what we can measure is the correlation function between the temperatures here and there and there and there and so on. We can calculate the correlation function. How much are the temperatures correlated at different distances from each other on the sky? And that boils down to a calculation very similar, very analogous to calculating the correlation function of the product of two quantum fields evaluated at two places in space but the same time. And according to the usual operator framework for quantum field theory, we would have to calculate this. Quantize the field, so these guys get hats, and then those field operators, you have to take the product of the two and then calculate the vacuum expectation value of that. Where one still has to identify what the vacuum state is, what the state is that the system is in. It may not even be in the vacuum. So this is, roughly speaking, the method that we will follow in most of the course. And that is advisable to do it this way because then we know what state really to put in there and what mode functions to use for this and so on. There are a lot of choices, lots of decisions have to be made, lots of things can be understood while calculating these things. But Feynman has a shortcut. It's just unguided. The shortcut doesn't tell us how to make those many choices. Like what is the vacuum state, which is the state of the system, and mode functions, and so on. So Feynman's method would have it that we can calculate this 2-point correlation function, 2 points because it's just 2 fields. We can calculate this 2-point correlation function simply by using Feynman's probability theory. We say, let us consider all possible products of fields. We are summing over all fields. This is the path integral of all possible field configurations. We take the product of the fields, multiplied with the probability that they actually occur. Right? So this would be the probability, or really probability amplitude, for particular field evolutions to occur. And then for those field evolutions, we calculate the product, and we sum over all possibilities. So the actual multiplied with the probability for this actual to happen, and then we sum over all of them, and that's a normalization of it. And that, too, in principle, gives us the 2-point function. It's just that the path integral is held to define explicitly. And it in calculating these things perturbatively, and that's the only way to do it, involves all the same questions, all the same choices, all the same identifications to be made as if we do it the operator way. It's just more obscure this way. At least nobody has really figured out how to make it clear in this context. So in principle, you get the same equations, but it's hard to make the choices right. So we'll go this way. But at the end of the course, I will show you how to calculate this sort of thing, especially if there are interaction terms and how we get to Feynman rules, Feynman graphs. Just for those of you who may not know about Feynman graphs from another course, and since this is a course on quantum field theory, I can't let you go without Feynman graphs, right? So okay. Okay, so that's as far as we got today. Okay, see you on Friday.